Let's dive into imagination. The year is 2500. The first space probe to leave our Milky Way galaxy is finally departing the orbit of the star at the galaxy's outermost edge. A historic celebration watched live by many. The name of this probe is Wanderlust I. Its target and mission: to reach our nearest neighbor, the Andromeda Galaxy. But while all the spectators are celebrating this event, something strange happens. Yes, this is a collision moment. The viewers and scientists watch in shock as the probe's midsection bends inward. Its metal deforms and tears, and some parts completely disintegrate. The probe's wreckage scatters into space, begins spinning in the void, all systems offline and dead. So whose fault is it? Wanderlust I was unexpectedly damaged by a black hole. Yes, the scenario I just described to you might be fiction, but small black holes, those with very small masses, might not be fiction. Can this be proven? It could be possible. Maybe they are out there, wandering around our galaxy. Maybe we have already captured evidence of the existence of these small black holes. I am Jeki, and you are watching Jekio. Come. Descend with me into the labyrinths of darkness and unravel the mystery of these primordial black holes. What are they? Where do they come from? The real question on everyone's mind. Should we be afraid? Now, I would like to begin by giving you a brief piece of information about black holes. All scientists and many people also refer to these small black holes as black hole rhinoceroses because they could have a similar mass structure. In fact, they once thought this was impossible. Until the 1960s, we knew one way how a black hole formed. Yes, black holes are the result of the collapse of stars. This was the evolution of a star, perhaps a star with a mass at least 20 times that of our sun running out of fuel, transforming into a supernova, exploding, and ending its life. As a result, all the matter exploding from this star dissolves and begins to collapse, and because it cannot escape the force of gravity, it leaves behind a dense object. That object is a black hole. This star turns into a black hole, and since this black hole was born from a star, it becomes a stellar black hole. Of course, not every star dies this way and evolves into a black hole. If these stars have a mass less than 20 times that of the sun, they also explode as supernovae. But this collapse is not powerful enough, so they do not turn into a black hole. Instead, we observe that they evolve into a neutron star, an extremely dense, tiny celestial object composed almost entirely of neutrons. From this, we can better understand that there is a limit, a certain size, for the formation of a stellar black hole. Let's explain this boundary. For example, compared to the largest stars, they cannot be larger than them, at most a few hundred times the mass of our sun. At the same time, they cannot be smaller than a few times that. So, why have we begun to entertain the idea that smaller black holes, which we once considered impossible, might exist? The strange part is that this thought lies in our desire to discover ones much larger than what we deemed impossible. Today, an important piece of information we have detected is that we know a massive black hole, a monstrous beast, lies dormant at the heart of almost all large galaxies. In the 1960s, we were just beginning to discover these immense-looking beasts. The first quasar, a very bright, reddish galaxy center, was detected in 1963, initiating a golden age of black hole analysis that lasted nearly a decade. The first thoughts about a giant black hole orbiting a galaxy exactly began in 1971. Over the years, as examinations and analyses continued, more evidence for these supermassive black holes emerged. And we saw that they were incredibly large, hundreds of thousands to billions of times more massive than our sun. The important question scientists asked was, how do they form? Technically, while it seems possible for a stellar black hole to grow by consuming mass after the star's mass ends, this idea began to lose its validity when examples of supermassive black holes from the early universe started appearing in more distant images of the cosmos being studied. Because with the possibilities of that time, there was no better explanation. Then the James Webb Space Telescope was invented, launched into space on December 25, 2021, and becoming operational in 2022, we now knew we would observe regions farther away in more detail than any previously sent telescope had seen or detected. The journey had begun, and the mission was underway on much more distant stars in space. Yes, James Webb did what it promised. The detected small red dots represent galaxies with massive black holes thought to belong to a time just 500 million years after the Big Bang. Scientists' analyses determined there wasn't enough time for stellar black holes to reach these sizes. The only possibility was unless they consumed matter faster than the laws of physics allow. Of course, there are many scientists who are not sure about this detection, and they think there is an alternative theory. Another recent discovery by James Webb may have confirmed this is correct. When considering the birth of a black hole, the key point is density. If we think the density is high enough, the mass becomes so compact that the gravitational field at its location passes a tipping point, and the speed required to escape it becomes impossible. That is, it would need to exceed even the speed of light. Of course, there is no real way to overcome such gravitational power. But wouldn't it be interesting if it weren't this way? Imagine being able to observe the interesting, physics-bending conditions at the heart of a primordial black hole, and then talk about this magnificence. Yes, let's continue studying black holes. As I said before, black holes are intensely compact with extreme density. The important question: how could matter become so dense in the earliest moments? This requires an enormous amount of dense energy. Almost enough energy to overcome the force that prevents electrons or protons from getting too close together and suppresses the electromagnetic force. Then there is neutron degeneracy pressure, a quantum mechanical force stating that two subatomic particles, two neutrons, cannot occupy the same place at the same time. We know that neutron stars are not dense enough for their gravity to overcome this pressure. Yet their density cannot be ignored. For example, imagine a spoonful of this matter. It would weigh almost as much as Mount Everest, over 900 billion kilograms. For a black hole to form, forces capable of squeezing all of Mount Everest into a teaspoon and much more must exist. In fact, for Mount Everest to become a black hole, it would need to be compressed into an area 1,000 times smaller than an atom. In the universe as it exists today, such forces only occur under very special conditions, inside collapsing stars that become supernovae. However, in the past, this was not always the case. Let's go to the very earliest moments of the universe, that first second after the Big Bang. At that moment, these pressures emerged, but only for a brief period. In this hot, dense moment, the distribution of matter was not just homogeneous or evenly spread. There were areas of high particle density and areas of lower density. Scientists' theory is that in these dense regions of space, primordial black holes could have formed directly from matter, essentially skipping the stellar stage altogether. This isn't a new theory. In fact, this surprisingly developing process has been termed primordial black holes. This event was first predicted as a hypothesis by Yakov Zeldovich and Igor Novikov in 1966. What's truly interesting is the possibility that they could have been born with masses nearly 100,000 times larger than our Sun's mass. This possibility, especially considering the billions of years available for growth, provides sufficient evidence to explain the supermassive black holes we observe today. Actually, they didn't have to be born gigantic. They could have formed at smaller sizes too, for instance the size of a single atom, with a mass comparable to an asteroid, or as small as a proton, with a mass only as large as a rhinoceros. Hence, the so-called black hole rhinoceroses. However, this was exactly 13.8 billion years ago. And today, there are two problems with the theory that such small-diameter black holes could still exist. The first is Hawking radiation, Stephen Hawking's theory, which essentially posits that black holes slowly shrink over very long time periods by emitting very long wavelength radiation. This theory tells us that, in all likelihood, all small black holes should have evaporated by now. The second problem is that we haven't yet proven whether primordial black holes have truly existed until now, meaning we've never seen a black hole form from interstellar dust. In fact, it's more accurate to say we hadn't seen one until recently. Let's come to July 2025. NASA's James Webb Space Telescope reported detecting what are thought to be two early disk galaxies colliding with each other. But the strange thing was that there was a supermassive black hole directly between them. And not at the center of either galaxy alone, they had their own supermassive black holes, making this third one completely inexplicable. The team that detected this suggested that this black hole formed in its orbit, born from the direct collapse of a gas cloud. However, This is not the only evidence that these black holes can simply appear under the right conditions. QS01 is a massive black hole detected by the Webb telescope. But the surprising thing is that it lives in a very small galaxy. Scientists' analysis revealed that while it contains heavy metals, it is extremely poor in all elements other than hydrogen and helium. This small galaxy possesses less than 1% of the oxygen found in our galaxy. And scientists stated that this is one of the systems in the early universe that has undergone very little chemical evolution. This tells us a lot. Stars only produced these elements in their earliest times, so their absence in QS01's galaxy indicates that very little star formation has yet occurred. Regardless of where QS01 came from, it is significant evidence that it was likely not born from a star. While the examples we've given so far are not definitive proof, these two examples strongly favor the idea that the early universe could have created primordial black holes. In fact, these findings could explain where all massive black holes come from. If we accept these theories as correct, then it is almost certain that super small black holes also existed in the early universe in the past. Looking at it, they all seem to have vanished, right? By now, they should have evaporated? Well, according to another emerging theory, maybe they haven't. When analyzing the amount of gravitational force in the universe, there is much more than there should be. Scientists' thinking leads them to conclude that there is extra matter surrounding galaxies in large rings. They call this dark matter because it is a ghost we cannot observe. So what else could carry this seriously substantial mass? It is not visible. The general assumption is dark matter. Black holes, especially structures formed directly from interstellar matter, without forming their own accretion disk. Of course, scientists have investigated and analyzed this idea. There is no evidence yet for potential super black holes around our Milky Way galaxy. If there were, they could swallow the stars in our galaxy one by one. However, small black holes, our so-called black hole rhinoceroses, would be very difficult to detect by known methods. But we cannot say they are not there either. The only thought is that all of them should have evaporated by now. Of course, we cannot say this situation is definitely so. In April 2024, a paper published in the Royal Astronomical Society's Monthly Notices journal found that at certain levels, Hawking radiation could slow down significantly, even stop completely. This thesis suggests that small-diameter black holes could shrink and shrink, eventually stop and vanish. If we assume this thesis is correct, we can think that black hole rhinoceroses could be out there. Scientists think dark matter surrounds our galaxy in a large ring. What if instead they were all small black hole rhinoceroses? There could be millions and millions of them, invisible and deadly. A black hole minefield we might one day encounter if we attempt to leave this galaxy to explore another. Here, we might be trapped without even realizing it. Of course, space exploration has many dangers of its own, but it is more than unsettling to think that while journeying into the darkness, we could be on a collision course with a small, microscopic black hole with the mass of a rhinoceros, or that one might be traveling through space, coming towards us. I hope we find evidence that this theory is not correct. Or at least, I'll forget the idea of leaving the galaxy. I think I'd prefer to stay home.